All right. Hello. Morning, everybody. Let me go ahead and start the clock here so that I don't run over again. Let's make sure that everything's okay. Okay. Um, well, like I said, please make sure then that you if you have any questions about the videos, you make sure you ask. Okay, folks. Don't hesitate to do so. Make sure you email me, and I will answer the emails, like I said, on the following video. So if you have questions about today's lecture, please email me, and then or actually, if you have any questions about any of the lectures, email me, and then what I'll do then is I'll answer the questions on the following video. So I haven't had any questions yet. Only about a few of you have been watching the videos. I've been checking in. Please make sure then, like I said, watch the videos. Don't put them off till the end. Is starting on the 5th next I think next Tuesday, I believe. So let's see, we start again. Let's see, let me check really quickly. Yes, so starting next Tuesday, on Tuesday, I hopefully will be done with chapter 14. I'd like to get started with chapter 15 on that day. So please make sure you watch these videos. Okay, and then like I said, ask questions. Email me the questions and I will answer them. Okay. All right. Let's go ahead and let's get started then. Let me go ahead and share with you the screen. Where we left off with yesterday is that we were able to take a look at what how we can define acids and bases. We defined Kw. We talked about how we can use Kw to find then the concentrations of hydrogen ions and hydroxide ions in solution. We then talked about how we could use the value for the hydrogen ion concentration to determine then whether and then compare that to the hydroxide ion concentration, and then determine then whether the solution is acidic or basic. And I gave you some general guidelines in order to make that determination. Okay. All right. So what we're going to do then is I would like to go ahead, and we were able to at this point then we were able to talk about the how we can do the calculations. Okay? So if we are given the concentration of a either the hydroxide ion or the hydrogen ions, okay, we should be able to first and foremost determine then whether the solution is acidic, basic, or neutral. Okay. Now I gave you some of those. I gave you the guidelines yesterday. And I'll sum them up for you again today. So make sure that if you didn't get them yesterday, make sure you get them down now. Okay. So if we can compare the hydrogen ion concentration if we can compare, we saw then that if we have the hydrogen ion concentration, sorry, let me go ahead and do this again. We have the hydrogen ion concentration, okay, and we said then that the hydrogen ion concentration, if the hydrogen ion concentration is equal to the hydroxide ion concentration, we know then that the solution is going to be neutral. Okay, so and this can only occur when both are equal to 1 times 10 to the minus 7 molar. Okay, so when we have a concentration of hydrogen ions and hydroxide ions that are equal to each other and they're equal to 1 times 10 to the minus 7, we know then that this solution, and we talked about this, will be a neutral solution. So this is a neutral solution, and as such then, the solution then is neither acidic nor basic. Okay? All right. So from there, then we said then that if, and the second instance here, if the hydrogen ion concentration is greater than 1 times 10 to the minus 7, which is neutral. If the hydrogen ion concentration is greater than that, then we know that the hydroxide ion concentration has to be, if that's the case, less than 1 times 10 to the minus 7. And the reason why this is true then is because remember, we said then that the water dissociation constant, Kw here, is going to be equal to the product of those two concentrations. Okay, we talked about that. And that both will be equal to 1 times 10 to the minus 14. This number here will always has to be constant. That 1 times 10 to the minus 14 has to be constant. And it's because of this right here, because of this value for Kw, because of this expression here, we know then that if the hydrogen ion concentration is greater than 10 to the minus 7, then the concentration of the hydroxide ion concentration has to be less in order for us to achieve then, when we multiply those two together, a product of 1 times 10 to the minus 14. Okay, so if this is true, okay, if this is true here, then what we say about this solution then is that it is an acidic solution. Okay, so if we have then a situation with the hydroxide ion concentration is less than 10 to the minus 7 and the hydrogen ion concentration is greater than 10 to the minus 7, this then is going to be an acidic solution. Okay? All right, so let me go ahead and write that down. It will be an acidic solution. Okay. All right. So finally then, a basic solution. What would a basic solution look like? Well, let's take a look at what a basic solution would look like. A basic solution then, if you can kind of follow this, then the basic solution then would have to have a hydrogen ion concentration then, which would have to be less than 10 to the minus 7 molar, okay, and a hydroxide ion concentration, which will be greater than 1 times 10 to the minus 7 molar. Okay? So this would be a basic solution here. Basic solution is a solution in which you have more base than acid. And I think this makes sense. Okay? So if we take a look at this here, okay, we know then that when these two concentrations are equal to one another, we have a neutral solution. Neither one of those is greater. Neither one of those is greater than a larger amount. However, if you have more hydrogen ions, okay, and remember, going back to the Arrhenius acid-base theory, and this is why when we learn the two theories of acids and bases, and I told you we'll be using them interchangeably. When we talked about the Arrhenius acid-base theory, we defined an acid as any compound that can produce hydrogen ions, and a base as any compound that can produce hydroxide ions. So imagine this: if you have a solution in which the hydrogen ion concentration, which represents the acid, and the hydroxide ion concentration, which represents the base, if you have a hydrogen ion concentration that is greater than the hydroxide ion concentration, you have then more acid. You want to think about it in that way. So you have more acid in solution than base, which makes the solution acidic. Okay. On the other hand, if you have a solution in which the hydroxide ion concentration, which again is the base, okay, is greater than the hydrogen ion concentration, which is the acid, that solution then tends to be basic. There's more base in that solution, and therefore it makes it basic. And that's how you should understand this right here, and that's what you should be looking at. Okay, so this basic generalization here can help you to determine then, without having to do any calculations, determine then whether a solution is acidic, basic, or neutral. Okay. All right, so looking at this solution here, we see then that we have a hydroxide ion concentration. So this is a hydroxide ion concentration. So we see that we have a hydroxide ion concentration that is greater than 10 to the minus 7. Okay, this is greater than 10 to the minus 7 molar. 10 to the minus 5 is bigger than 10 to the minus 7. So therefore, we already know that the solution then has to be basic. Okay, so we know then that this is a basic solution already, based simply on our comparison here. We didn't have to do any calculation, but based upon our summary here, our general summary here, we know then that this solution has to be basic. So we can answer this question before we even do any calculations. Okay? All right. So with that said, though, they ask us to find here the hydrogen ion concentration. Okay? So if we know the hydroxide ion concentration here, that's what we know. Okay? To find the hydrogen ion concentration, we're going to make use of this formula right here. Okay? So we know then that the hydrogen ion concentration times the hydroxide ion concentration will give us the ion product constant here for water, which is 10 to the minus 14. Okay? All right. So we know that. So let me go ahead and do that real quickly. Sorry. 10 to the minus 14. Okay. So we know that. So here we know, we also know the hydroxide ion concentration. So solving for the hydrogen ion concentration is pretty straightforward. You just divide both sides by the hydroxide ion concentration, and we should get our answer. Okay. All right, so let's go ahead and let's plug in our numbers here really quickly and then solve for it. So it'll be 1 times 10 to the minus 14 all over 1.0, sorry, times 10 to the minus 5. And then we get our answer then as 1.0 times 10 to the minus 9 molar. And we clearly see here then that that number is less than 10 to the minus 7. And so therefore, again, this confirms for us that the solution will be basic. Okay? So again, we can answer this question even before we do any calculations, but this, our hydrogen ion concentration here should confirm for us that the solution will be basic. Okay. All right. So that's where we left off with yesterday. What I would like you to do now, so you'll have to do this on your own paper. So please make sure you do this on your paper. Okay. Take a look at number 3 in your problem set. Okay. So let's take a look at number 3 in your problem set. And I would like you to work out both of these problems on your paper. So take about 3-4 minutes to work out number 3 on your problem set. Okay, so take a look at number 3. So we're doing the same thing here. I give you 2 solutions. The first solution has a hydroxide ion concentration of 1 times 10 to the minus 7. And the second one has a hydrogen ion concentration of 10.0 molar. So determine whether the solution is acid, base, or neutral, and then calculate for the other component of the reaction. Okay, so take about 3-4 minutes to calculate for answer the questions, and then we'll go over this together. Okay, so go ahead, take 3 minutes to work this out. Okay, let's take a look at this problem here. I'm going to pull up my whiteboard here really quickly so I have more room to work this out. So let's go ahead and do that. So there's my whiteboard. Okay, let's go ahead and let's take a look at the first one. Okay, so for the very first problem then, okay, we are told then that we have a hydroxide ion concentration. So we're given the concentration of hydroxide ions. We're told then that the concentration of this solution has 1.0 times 10 to the minus 7 molar. Okay, folks, I hope you recognize this already. Okay, I hope you recognize that based on this concentration here, first of all, what we should be able to do then, and hopefully you won't have to do any calculations, we should already know what the hydrogen ion concentration is going to be for this solution. It will also be 1 times 10 to the minus 7 molar. Okay? Again, you can do the calculations, but hopefully you recognize then that this represents a neutral solution, because if you have 1 times 10 to the minus 7 molar concentration of hydroxide, you know that you have to have 1 times 10 to the minus 7 molar concentration of hydrogen ions, which gives us then a neutral solution. Okay? So those are the answers for number 1. We don't have to do any calculations for that one at all. Okay. All right, let's take a look at the next one. Okay. All right, so for the second one, we are given this time a hydrogen ion concentration of 10 molar. Folks, I hope you take a look at that and you recognize then that this is a concentration of hydrogen ion that is much greater than 10 to the minus 7. Okay? And remember, if the hydrogen ion concentration is greater than 1 times 10 to the minus 7, we have an acidic solution. So we can say that already without having to do any calculations. So we have an acid solution here. Okay. All right. So with that said, then we need to calculate then for the hydroxide ion concentration. We're given the hydrogen ion concentration. We need to calculate for the hydroxide ion concentration, which, given our formula, we're going to take the concentration of the hydrogen ions, okay, and we're going to divide Kw by it. Okay, so that's how we would calculate and determine hydroxide ion concentration. So let's go ahead and calculate. We have 1 times 10 to the minus 14 all over 10. Okay. So therefore, that would give us then a value of 1 times 10 to the minus 15 molar as the hydroxide ion concentration, which, if you notice here, is much smaller than 10 to the minus 7, which confirms for us again that this solution is an acidic solution. Okay, so hopefully you got that. Hopefully, please compare your answers and take a look at that. Okay, and be able to work that out. If you can't, please again make sure you ask about it. Email me and ask about it, and that way then I can work out a few more for you. I think I assigned set A. I suggest that you set A and set B. Set C, I'll suggest you do that tomorrow. But practice this here, folks. Practice this here, and then that way then these calculations will be pretty straightforward. Okay. Also practice the looking at a solution, the concentration of the solution. If you're given the hydrogen ion concentration, hydroxide ion concentration, be able to answer questions about that without having to do any calculations. Okay. But But let's go ahead then, and the calculation should be straightforward. I think the issue then is going to be working out conceptual problems such as this one here. Okay, so take a look at this particular problem here. Okay, let me give you a couple minutes to take a couple minutes to explain what this problem's asking you, and understand then that you will be asked problems like this on the AP exam, where you're not asked to do any calculations, but you're asked to consider what's going on. Okay, so let's take a look at what we have here. Okay, so we are told then that at 60 degrees, kW is 1 times 10 to the minus 13. Now recall, and make sure you remember this, remember then that we were given kW before. We learned kW. We were told then that kW was equal to 1 times 10 to the minus 14. But remember, that was when the temperature was at 25 degrees Celsius. So kW, when you have kW, and that's what's typically given to you as 1 times 10 to the minus 14, that is a constant, that's the equilibrium constant when the temperature is 25 degrees Celsius. And then remember, the equilibrium constant is dependent on the temperature. We learned that back in chapter 13. So here we are given then a new value for kW. Yes, it is a new value for kW. Why? Because now the temperature is at 60 degrees. So at 60 degrees, kW then is 1 times 10 to the minus 13. So make sure you understand that's what they're that's what they're emphasizing here. Okay, so if you take a look at this, this is the water dissociation. This is the dissociation autoionization of water. Okay, two water molecules produce then hydronium ion and hydroxide ion. Okay, so that's the autoionization of water. But now this process is not taking place at 25 degrees Celsius. It's taking place at 60 degrees Celsius. So that's why the kWs are different. So what they want us to do here, okay, is based on this value for kW at 60 degrees Celsius and this value of kW at 25 degrees Celsius, determine then whether this solution, whether this reaction here is exothermic or endothermic. It seems like a fairly daunting task at first, okay, but let's consider what we have. Okay, so let's go ahead and analyze this question real quickly. Okay, all right. So what we are given here then is we're told essentially that the temperature has increased. So we're going from 25 degrees Celsius to 60 degrees Celsius. Okay, so let me go ahead and let's write down the equation for kW let's write down the law of mass action for kW first. Okay, so the law of mass action for kW, let's go ahead and write that down, and then we'll use that to answer this question. Okay, so sorry, let me go ahead and do this here. Okay, so kW, remember, is simply then the hydrogen ion concentration times the hydroxide ion concentration. Okay, and that should be over 1. So let's make sure you keep that in mind. That should be over 1. Okay. Because why? Because remember, water in the liquid state, okay, is we don't include that. Okay. All right. So let's take a look at what happens here. So at we are increasing the temperature. So let's make sure you keep that in mind. So we are increasing the temperature. Temperature is going up. Okay. So if we are increasing the temperature, what does that result in? That it results in an increase in heat. We are adding heat to this solution here. We are adding heat to this reaction here. We are adding heat to this reaction. What happens to kW as we add heat? Look at this. It goes from 10 to the minus 14 to 10 to the minus 13, which means then kW increases. Okay. Now, how can kW increase? Well, kW can increase if both of these values here increase. That means then, remember, if kW goes up, that means that these two go up as well. So remember that when kW is 10 to the minus 14, both of these were 10 to the minus 7. So you can imagine then for kW to increase to 10 to the minus 13, that means both of these also have to increase. Now remember, hydronium ion here represents the proton. That is what we represent as the proton here. So it's basically hydrogen ions. It's hydrogen ions and hydroxide ions. We probably should have written this, and maybe I should do this. We probably should have written this as H3O, as hydronium ions and hydroxide ions. Okay, but well, let me go ahead and do that because that may confuse some of you. Okay, so let me go ahead and rewrite this really quickly. This is going to be then H3O hydronium ion. Okay, so the autoionization of water. So with that said, then, if kW increases to this value, if kW increases, that means both of these also must increase. So as we increase the heat, the amounts of both of these increase. That means then, remember, that means then the reaction is shifting towards the right. And the only way that the reaction will shift towards the right is if heat is a reactant. Okay? If heat is a reactant, okay, if you increase the heat, so if heat is a reactant, if you increase the heat, that is what's going to shift the reaction towards the right. So if you increase the temperature, heat goes up. You're increasing the amount of heat. The only way that the amount of product here will go up is if heat is a reactant. Remember, Le Chatelier's principle tells us then that the reaction will shift in the direction away from the disruption. So we are disrupting this reaction by adding more heat on the left-hand side, which means then the reaction will shift towards the right-hand side to produce more hydronium ions and hydroxide ions. And if that's the case, that's when Kw is going to get bigger. Kw will get bigger. So therefore, if heat is a reactant, what does that mean for us? That means then that this reaction is an endothermic reaction. And so the autoionization of water then is an endothermic reaction because heat is a reactant. When you increase the amount of heat, you shift the reaction. Equilibrium will shift towards the right, towards the product, okay, causing the Kw to increase. And so based simply on that, folks, and all they gave us here was the new Kw, okay, at the new temperature here. They probably should have given you, but they're assuming that you know this. Okay, so just based on these two pieces of information here and here, okay, new Kw at new temperature, we should be able to come up with this answer as endothermic. This is a conceptual question that gets you to think about Kw and Le Chatelier's principle, which we learned in the last chapter. So this is an application of Le Chatelier's principle to the autoionization of water. Okay. All right. So I think the second question will be pretty straightforward then. I think let's go ahead and do that really quickly. Okay. So with that said then, if we know then that Kw is going to be equal to the hydrogen ion concentration, or the hydrogen ion concentration, which we will do as hydroxide, hydronium. Okay. And so if we know that, and if we know that Kw, we're given Kw here as 1 times 10 to the minus 13. Let's go ahead and calculate for it. These two have to be equal at this temperature. So therefore, we will refer to that as x times x, or x squared. Okay. And so that's solving for x. Let me go ahead and do this here. Solving for x, taking the square root of both sides. So if you see this, you get a concentration then that is, I have here 3 times 10 to the minus 7 molar, okay, which is a greater value than the hydrogen ion and hydroxide ion concentration at this value, at 25 degrees Celsius. So we have increased both, we have increased both the hydrogen ions and the hydroxide ions for this particular problem. Okay, so when we increase the temperature, we are increasing the hydrogen ion and hydroxide ion concentration as well. So last question for you, and I would like you to share this with me on your paper, okay? And just type it into the type your answer into the Edpuzzle answer box here, and I'll give you a couple seconds to do it in just a moment. Is this solution acidic, basic, or neutral? And tell me why. So onto Edpuzzle here, answer this one question for me. Okay, is this solution now, this solution here with a concentration, and keep this in mind, this is concentration of hydrogen ions and the concentration of hydroxide ions, okay, which is now 3 times 10 to the minus 7. Remember, the hydrogen ion and hydroxide ion concentration up here, hydrogen ion concentration and hydroxide ion concentration here is going to be equal to 1 times 10 to the minus 7 molar. So we have increased the concentrations of both of those. Okay, and so the question here then is that, is this solution, and let me go ahead and ask this question, is this solution acidic, basic, or neutral? Okay, so is this solution acidic, basic, or neutral? And then tell me why. Okay, so go ahead, take about 30 seconds to answer that question here about this new solution here, this new solution at 60 degrees. Okay, so 30 seconds. Let's go ahead and see what you come up with. Okay, the question then is this solution acidic, basic, or neutral? Now, we said then, remember, for an acidic solution, the hydrogen ion concentration has to be greater than 10 to the minus 7, 1 times 10 to the minus 7, okay? And the hydroxide ion concentration has to be less than 1 times 10 to the minus 7. For a basic solution, for a solution to be basic, the hydroxide ion concentration has to be greater than 1 times 10 to the minus 7. And the hydrogen ion concentration has to be less than 1 times 10 to the minus 7. And for a solution to be neutral, the hydrogen ion concentration and the hydroxide ion concentration are both equal to 1 times 10 to the minus 7. That's what we said. But we said that that was true only if the autoionization, only if this reaction right here is taking place at 25 degrees Celsius. The solution now, the reaction now is taking place at 60 degrees Celsius, which means that we have a hydrogen ion concentration and a hydroxide ion concentration that is 3 times 10 to the minus 7. So some of you may be wondering, well, wait a second. That means that the hydrogen ion concentration is greater than 1 times 10 to the minus 7. That means it must be acidic. Or some of you might say then, well, wait a second. The hydroxide ion concentration here is greater than 1 times 10 to the minus 7. So that must mean the solution is basic. Who's right? Well, the answer there is neither of those two groups would be correct. The solution ends up being a neutral solution. Okay, so the solution ends up being a neutral solution. Why? Because the hydrogen ion concentration and the hydroxide ion concentration are equal to one another. And whenever you have the hydrogen ion concentration and the hydroxide ion concentration that are neutral, that are equal, you have a neutral solution. So yes, you have more of both of those, but they're still the same. Okay? You have the same amount for both, and so therefore that makes this new water solution at 60 degrees. It still has to be neutral. Just because you increase the temperature on water doesn't make the water acidic or basic. You still have a neutral solution of water. You boil water, that water still be neutral. Okay. All right, very good. So hopefully you got that. If not, then please make sure you reconsider what you wrote in the context of what I just told you here. And if you're still unclear on that, like I said, email me and I'll explain that to you. Okay, and I'll go over those points again for you. Okay, so make sure you keep that in mind. So this is a good question to ask. This question, I didn't get this question from the AP exam, but you can probably expect a question like this on the AP exam. Okay, all right. Let's go ahead then. Let's do another solution, another conceptual problem here involving acid-base solution. Okay, so take a look at number 4 in your problem set. Take a look at number 4 in your problem set. And what I would like you to do then is answer the question. Okay, if this is your reaction here, where you have a base here, so this is an anion base, and you mix it with water, you form the conjugate acid and the conjugate base here, which is hydroxide ions. Okay, which side will equilibrium favor? Okay, and which way will the reaction move towards equilibrium? Okay, and so this is what we call then a salt solution here. So this is an ionic compound. Let's write this for you. Okay, this is an ionic compound. Okay, and so when you dissolve this ionic compound, we can imagine that this ionic compound is going to be then I'm sorry, in a sodium anion. What will happen in solution then is that this compound will dissolve into sodium ions and the appropriate anion. Okay? And so the question this is asking is, what will if this anion then goes on and it reacts with water to form then the conjugate acid here and this base? Okay, in what direction will the equilibrium lie? So answer that question, but then tell me why. Okay, so this question is a little bit more involved than I think some of you may believe. But first of all, tell me which direction will equilibrium shift toward equilibrium lie, and which side will equilibrium favor? Will it favor the left-hand side here with the anion and water, or will it favor the right-hand side here? Okay, and then answer why. Okay, so which direction will equilibrium lie in, and also answer the question why. Okay, go ahead, take about a couple minutes to answer that question, and then we'll talk about it. Okay, so a couple minutes. Okay, well, let's take a look at this here. Okay, So the reaction is basically, and if we want to, let me go ahead and let's write out this reaction. This is going to be then the anion here. Okay? Since it's a base, it's going to accept a hydrogen from one of the hydrogens from the water molecule. Okay? So there's the hydrogen. Okay? So it's basically going to go in and it's going to pick up a hydrogen ion from water, and in doing so, it's going to form then, okay, the anion, this new acid here, content acid, and leaving us with the hydroxide ion here. Okay. All right, so what we have to do here is we need to compare this base here. Okay, we got to compare this base here with this base here. Okay, and so the question then is, which one does a better job of removing the hydrogen? Okay, so does the anion here going in and removing that hydrogen from water, or is it going to be the hydroxide ion here going in and removing that hydrogen? Okay. And so whichever one is the better base, whichever one does the better job of removing that hydrogen, that's the direction the reaction is going to shift it. Okay. So with that said, then this is the stronger base. Okay. This is a stronger base, and understand why is this the stronger base? There is no base stronger than hydroxide. Okay. The hydroxide ion. Now remember, if you looked at the list of all the strong bases that I gave you last semester, and again, no one has emailed me about providing that list again, and maybe I should, but please email me, let me know. But if you looked on that list of strong bases, all of those strong bases were hydroxide bases. Okay, that means then they were all bases that had the hydroxide ion. Okay, so there's no base stronger than the hydroxide ion. Okay, so with that said, then hydroxide does a much better job of removing the hydrogen ions than the anion here does. And that means then the reaction here will shift towards the left. Okay? The reaction is going to move towards the left. Okay? Equilibrium then is going to favor that direction. It's going to move back in that direction. Equilibrium is going to move back towards the left. The reason for that then is because hydroxide is a stronger base than the anion here. Okay, that's the reason why. Okay, all right. So hopefully you're able to get that. If not, then please again make sure you you try the homework, okay? and then make sure you come by and you ask. Okay, all right. So with that said, that's number 4. What I'd like you to do then is well, I'm sorry, that means I answered number 5 for you as well. So let's go ahead and let's take a look at number 5 really quickly. Number 5 then to ask you then does that make then A minus a strong base or weak base? We already saw then that it's going to be a weak base. Again, whenever you see hydroxide, you guys, whenever you see the hydroxide ion, that means then wherever it came from, okay, you have a strong base present. Okay, so this may have come from sodium hydroxide, lithium hydroxide. Regardless, you have the hydroxide on here. That will always be the strongest of the bases. Okay, that'll be your strong base. Okay. All right. Now, let's take a look at the next question. So let's take a look at the next question, and I want you to take about. I think this may take you about 4 or 5 minutes to consider this here. But let's take a look at number 6 here. Let's take a look at number 6 here, and what I'd like you to do is, so I have given you here different bases. Okay, so you have 4 different bases here. Okay, and I want you to put them in order from weakest to strongest, And then what I'd like you to do is tell me why you came up with that answer. So not only will please put them in order, but also explain your answer, folks. Okay, so this is again conceptual. There's no real calculations that you have to do here. But what I would suggest you do though is go ahead while you do this problem. Okay, I would suggest you take a look. You'll need table. I think it's table 14.2. 14.2 on page 658 of your textbook. Okay, so look at table 14.2 on page 658. You will need that to help you. You will need that to help you do this problem. Okay, so go ahead and take about 5 minutes to work through this problem here, and then I'll help you through it. Okay, and then we'll compare answers. Okay, so take about 5 minutes, and then when I see you back here, we'll work out this problem together. Okay. All right, folks. Hopefully you tried it. I know this problem is actually a little bit more difficult than what it seems. Okay, it looks a little bit more difficult than what it seems. And so what I'm going to do then is really quickly, I'm going to open up my whiteboard again, and let's take a look at what a few things here. So again, hopefully you use that the information on table 14.2 to help you with this. Okay, so let me go ahead then. Let me share a couple things with you here. Okay, from that table. So first of all, let's go ahead and let's take a look at what they give us for for hydrocyanic acid. Okay, so Ka for HCN is they give it to us as 6.2 times 10 to the minus 10. Okay. Now remember, what this Ka refers to then is this process here, where we have HCN, the equilibrium, where HCN breaks down to hydrogen ions and cyanide ions. Okay, so there it is. Okay, that's what this Ka refers to. So that means then the Ka for acetic acid, so the Ka for acetic acid, I'm going to go ahead and give this to you, is 1.8 times 10 to the minus 5. Okay, which is this process here, which is of the dissociation, 4C2H3O2. That Ka refers to this equilibrium here, where you form hydrogen ions and C2H3O2 anion. Okay, so that's what we have then for these. So this is from table 14.2. Okay, now you don't see the table 14.2 listing the Kas for HCl. Okay, and so that means then, okay, the chlorine ion comes from this process here, where the hydrogen ion breaks down to form the chloride ion. Okay, so what you need to make sure you understand then is that the anions here that they are referring to comes from the dissociation of these acids here. So there's the cyanide ion, there's the acetate ion, and there's the chloride ion. Okay, so they're asking you to compare these anions here as bases. They're asking you to compare these anions here as bases. Okay, but they give you the Ka values here. Okay, now, with that said, though, they don't give you the Ka for hydrochloric acid. Okay? But we know that hydrochloric acid is a very strong acid, and I will give this to you. You can find it, okay? But I'll give this to you here. The Ka for hydrochloric acid is about 1.3 times 10 to the 6th. Okay? 10 to the 6th. That's a huge number. That is much greater than 1. Okay, so this is the Ka for hydrochloric acid, which is what makes it a very strong acid. Okay, all right. And then finally, let's take a look at water. Okay, water then, the autoionization of water, which means that this is the process which forms then, okay, hydrogen ions and water there. Okay, all right. And the Kw here, Ka for this one, or the constant for this process here is 1 times 10 to the minus 14. Okay, all right. So taking a look at this here, how do we put these in order? Okay, so I'm going to go ahead and highlight this here. Okay. Okay. I'm going to go ahead and highlight that there, and then let's take a look at this here. What we have to consider then is let's consider the strength this here. The larger the Ka, the stronger the acid. But the larger the Ka, which means then the more the reaction favors the right-hand side. That means then you will produce more product. Okay? So the larger Ka, the stronger the acid. The stronger the acid, the more it dissociates. Okay? Which means then very little of the reverse reaction occurs. Okay? Very little of the reverse reaction occurs. And that's what you want to make sure you keep that in mind as we go through this. Okay? All right, so with that said then, if you consider this, this is a huge Ka, which means then the reaction absolutely favors the right-hand side, which means then, and if we, and I'm just going to the side here, let's draw what this means here. Okay? What the equilibrium constant tells us then is that the reaction here highly favors the left-hand side with very little of the reverse reaction occurring. That's what this Ka tells us right here. Okay? And so with that said, then if we take a look at this here, this is also fairly large compared to that Ka, which means then you have more reactant turning to product and less product returning back to reactant. And then finally here you have very little reactant, most of it going back that way. Okay. Now I should probably extend this one and exaggerate this one just a little bit more here because we don't want to. I don't want to. There's a false equivalence here. Okay. All right. So with that said, then you have more of the reverse reaction happening. Okay. This is what the Ka is for telling us, and I want you to make sure you keep this in mind. Okay. Each one of these arrows here represents the direction of equilibrium. Each one of these arrows here represents the direction of equilibrium, which we obtain from this Ka. This is the information that the Ka is telling us about the reaction. Okay. Now, but what does that tell us about the base? That means then the more the reaction shifts back towards the left-hand side, the better that base is. So we're going to compare this base to this base to this base. Now, if you notice between those three bases here, very little of the reaction shift towards the left here, which means then the chloride ion is not very good at shifting the reaction back towards the left-hand side. Okay? Which means then the chloride ion is not good at picking up the hydrogen ion or accepting the hydrogen ion to be back here. So therefore, the weakest of the bases is going to be the chloride ion because the reaction doesn't shift back towards that way. Okay? Now we can compare these two bases then. That means then between these two, acetate is less, it's not as good as cyanide as at shifting the reaction back towards the left. Okay, which means then the chloride ion is going to be the weakest. Okay, and that means then the acetate ion is going to be next. C2H3O2, and the strongest of these then will be the cyanide ion. Okay, so that's the order of bases. Okay, so let me go ahead and clean this up really quickly. Sorry, guys. Okay. Now again, how did I come to that conclusion? C2H3O2. Let me go ahead and repeat that. Okay. We are looking at the equilibrium constants, the Ka values. We said then that the larger the Ka, the stronger the acid is. Okay, the stronger the acid is. The stronger the acid, the weaker its conjugate base will be. That was the general rule that I gave you in the last lecture. That means then this is a very strong acid, which means then its conjugate base is going to be very weak. A weak base, the meaning of a weak base is that it is not very good at accepting a hydrogen ion. It doesn't pick up a hydrogen ion very well. The stronger the base, the better it is at picking up a hydrogen ion. Okay, so the stronger the base, the better it is at picking up a hydrogen ion. Okay, so that means that of these three anions here, chloride's going to be the weakest. It doesn't do a good job of picking up a hydrogen ion. Then acetate, and then the cyanide, based simply on, and we can do that based simply upon these Ka values. And it's how you interpret these Ka values that will help you determine that. Okay, so it's these boxes here. It's what we have represented in each one of these boxes here that you need to make sure you try to understand. That we take from the Ka value. Okay. All right. That leaves us with water. Okay. And if you notice here, water does produce this base right here. And I had told you that hydroxide is the strongest base, of any compound, of any base. Okay. So you would be tempted to say then that water goes here. Okay, that water goes here. That water, since it forms the base, it goes here. But there's a problem that we have to consider here, okay? And that is water, remember, is neutral. The autoionization of water here means then that you have an equal amount of this ion and this ion. In each one of these cases here, you don't have an equal amount of the base and the hydrogen ion. You don't. Okay? Here you have an equal amount. So this means that this is a neutral solution. Okay, so that means then this is not going to be the biggest. Okay? Actually, what we're going to see the water, remember, the concentration here is going to be about 10 to the minus 7. Okay, 10 to the minus 7, which means then water actually fits right in between That's where water is going to be. Remember, water is an amphoteric compound, which means that it does do a good job at picking up hydrogen ions, okay? But it's not that strong. Okay, so the order then, the final order of base then is going to be chloride ion is the weakest, then water, then acetate, okay? And then finally then we have cyanide. Okay, and that is the order. Sorry, guys, and that is the order of the order of base strength. Okay, so this is the final order right here. That's your answer. Okay. All right. So please make sure you try to look at this and work through this again in your mind. You really have to make sure then that you understand how to interpret the values for Ka. That's why we are using Ka. We use Ka. We learned about Ka, what it is. We can use Ka to determine then the strength of the acid, but we can also use Ka here in this manner here. You have to learn how to interpret Ka and understand the information that it gives us as we go through this. Okay. All right. Unfortunately, I'm out of time. So what we'll do then is we'll work through another problem tomorrow. Tomorrow we'll continue going over this, okay? And we'll practice this some more. So please practice this on your own, but we'll practice this some more. We'll practice interpreting Ka values, and then we're going to start talking about how we can use Ka values to determine to do the equilibrium calculations that we did back in the last chapter, in chapter 13. Okay. All right, very good, folks. I will see you tomorrow with the new video. Please make sure then, like I said, as you go through these videos here, if you have any questions, don't hesitate to email me. Or if you don't get a chance to email me, make sure then come next Tuesday, you start coming by and asking questions about this. Okay. All right, folks. Very good. Have a good day. I'll see you tomorrow. Okay.